Hello and welcome to the MOOC on optical communications. In this module, we will discuss optical amplifiers. These components or devices, if you would call them, they are very important in a modern optical communication system. Now, the reason why an optical amplifier is important is just as why an electrical amplifier is important when you are looking at communication systems, because amplifiers allow you to amplify the signal. So, typically signals which are at the receiving end. So, at the transmitting end, when you transmit a modulated information on the carrier and then send it out to the receiver, the signals are quite strong. So, if you were to look at the energy in the sidebands, for example in a double sideband modulation, then the energy would be significant at there, as does the carrier energy as well. However, as this double sideband suppressed carrier maybe, for example, passes through the atmospheric channel, because of the losses and because of the noises that get accumulated, especially at the receiver end, what will happen is right at the receiver side, if you want to look at the energy would have been very small. A very similar thing happens when you take the optical carrier in the form of a laser and then modulate this laser in order to impress your data onto that, and then this modulated carrier travels through the optical fiber, and fiber introduces dispersion as well as loss. So, loss is of course important because it basically starts to reduce the signal amplitude or equivalently the optical power. So, it might come to a situation where the optical power that is received will be so small that it would essentially be buried inside the noise that you are going to look at. So, you are from the noise from which you are trying to extract the signal. We normally quantify how much the signal is powerful compared to the noise by defining a quantity called as signal to noise ratio. So, you want at the receiver a very high signal to noise ratio. You want it because your signal, which is very small in amplitude, if it is very small in amplitude, then it is almost impossible for us to distinguish the signal from the noise if the signal to noise ratio is very small. Now, one can of course mitigate this problem without the use of an optical amplifier. How would we do that? Suppose you have a carrier, so let us say this is there at your transmitter end, you modulate it, you send the information. Okay. So, let us say your fiber has a certain length, and then after that particular length, the optical power would have reduced to so much that you cannot detect it. That is, your APDs or the photodiodes will have a detectivity or the sensitivity below which the signal power would fall if the length of the fiber is large. So, if you do not want this length of the fiber, so if you do not want the signal to be lost in this in this process, and hence you want to recover the signal, you can simply reduce the length of the fiber. Okay. So, reduce the length of the fiber, detect the signal, amplify it, okay, and then maybe if you want to clean up the signal, you can also clean up the signal. Maybe signal is also suffering from some chromatic dispersion, so the bit boundaries have slightly enlarged, so you can actually reshape the signal. So, you can receive the signal, regenerate the signal, reshape the signal, you do all that, okay, and then send it on to the next span. Okay. Notice here what has happened, you have not used an amplifier. So, whatever that you have to work with, you have to work with possibly very low optical powers, and moreover the available or the span length that you are looking at will have to be limited, because if I increase the span length, that is length between the repeater and the transmitter, or between two regenerative repeaters if you are in the mid span of the link, then the distance between this span actually reduces. You do not want this, because reducing the distance means that you have to put in more and more regenerators. The number of regenerators simply start increasing if you do not have an amplifier, and you choose to work with this low amplitude or low power scenario. Okay. So, it is not advisable from the cost point of view. Moreover, if you do not have enough amplitude or enough optical power, it is not just you cannot regenerate the signal, you might also be suffering from other problems. For example, if you have multiple wavelength signals which you have multiplexed, okay, and then you have transmitted. So, at the transmitter there is sufficient power, but at the receiver, in order to regenerate the signal, you have to first separately take each signal out through each wavelength out through a wavelength demultiplexer, and once you have taken them through the demultiplexer, then you have to separately put a regenerative repeater. Okay. So, you see that if you do not have an amplifier, the length before which you have to regenerate becomes very small. If you had an amplifier, then you can go long distances without really amplifying, okay, or without really doing anything, and once the signal level falls right at the end of the first span, you can simply amplify the signal back to a desired level that you want. And it is always nice to work with signals at this level, where there is comfortable optical power, so that the further parts of the communication link are satisfactorily working. So what you need is an optical amplifier, and we are specifying something like optical amplifier. What is the difference between an optical amplifier and electrical amplifier? Except that they work at two different wavelengths, in theory there is no difference between an electrical amplifier and an optical amplifier. However, for optical communication systems, the development of optical amplifiers was a very significant step. In fact, before the optical amplifiers, the systems would normally look like this. So, you have a transmitter here, and from the transmitter you launch onto the fiber, it would propagate. Now notice there was no optical amplifier. So, what you had to do was you had to put a photodetector, right. So, you had to put a photodetector, from the photodetector receives. Once you have the photodetector, you convert from optical signals over here to the electrical signals onto the photodetector. Then you would amplify, regenerate, and then amplify, regenerate and reshape. Okay. So, you would do all these processes in the electrical domain because it was kind of easier to develop, or the technology for microwave amplifiers or electrical amplifiers was very mature in the early 80s, because of the developments in the microwave technology. So, you could convert from optical to electrical and do all the processing in the electrical side, and then put one more optical transmitter or an optical modulator. So, let us just put an optical modulator and then transmit once more. Okay. So, this block, which you can encapsulate from the receiver side onto the modulator side, would perform optical to electrical conversion, amplification and other processes, clean up the signal, and again from electrical to optical signal back. So, you have of course at this point an optical signal and at this point an optical signal, but in between there has been a bottleneck. Why is there a bottleneck? Because your optical to electrical conversion is a slow process, depends on the photodiode and the associated circuits, and whatever the amplification, regeneration, reshape that you have to do, you will have to do that in the electrical domain, and it is cost ineffective because you have to, after doing the electrical signal, after getting a reasonably clean electrical signal, you then have to remodulate the optical carrier. So, of course, you would also require a laser diode at this point. So, you have to, you see that at every span you have to put a laser diode, you have to put a modulator, you have to put all these things. So, clearly giving us a problem in terms of cost, giving us a problem in terms of speed or the distance between the spans, right. So, the distance was also a major factor because you could not go far too long, because if you went far too long, then you see that the optical power would have dropped considerably over here. So, the lesson out here is that around 80s people realized that if they have to increase the speed of operation, so at that time the optical speeds was not very high. Okay. However, if the demand for speed was always there, and if you wanted to go to a larger speed, then it was necessary to circumvent this bottleneck. Okay. So, optical to electrical and electrical back to optical is something that we would not want to have it, because it will increase cost, it will decrease speed, and it will also limit the distance. So, what is the solution? So, interestingly, two kinds of solutions came up. One was called as semiconductor optical amplifier. Okay. So, these are for short known as SOAs. Okay. And these work essentially on the principle of, very similar to a principle of a semiconductor laser. In fact, we will very shortly see the relationship between a laser and an amplifier. These semiconductor optical amplifiers was made out of the same materials as the semiconductor lasers, more or less they were made of the materials as the semiconductor lasers, and they were excellent in amplifying signals optically. So, what is the significant difference over here? You have an optical signal coming from a transmitter passing through the fiber. So, you have a signal that is completely optical, and then if you give this one to a semiconductor optical amplifier, what you would get would be an amplified optical signal. Okay. And this amplified optical signal you would get in the optical domain itself. So, there is no conversion of optical to electrical and back from electrical to optical. So, this in principle would have been a very nice solution, and in fact it was proposed as a nice solution, except that it did not work very well, okay, for various reasons that we will comment on later. But if you had this semiconductor optical amplifier, you give an optical input and what you get would be an amplified optical output. So, no electrical to optical or optical to electrical and electrical to optical conversion, and therefore the speed could be increased tremendously. As far as the cost is concerned, again the cost, well, in this case it is just doing the purpose of an amplifier. If you want to clean up your signals, you still have to do something else onto that one, but if you clean up is not what you are looking for, then this would also reduce the cost. Moreover, you can now increase the distance between the transmitter and the point where you put in the amplifier, because at that point you have still a little bit of an optical power which can then be amplified. So, if you were to follow up on how the optical power would go, let us say you launch a certain power Ptx over here, okay. So, this is the launch power, maybe you could call this as P in, but I just arbitrarily call this as Ptx. Because of the fiber, there is a linear attenuation up there, correct. So, the power basically goes down. I am plotting all the powers in the dB scale, and what is the loss here? Alpha f into L. So, the slope of this one would be alpha f. At this point, of course, the power that you are receiving will be Ptx minus alpha L, all measured in terms of dBm. How many milliwatts above this particular thing would exist. Now, this one can be amplified, okay. So, let us say at this point we put in a semiconductor optical amplifier of an appropriate gain, so that I can bring back the optical power to what it was originally to begin with, okay. So, at the transmitter side you have Ptx, and because of an SOA which has applied a gain G, now the total power has gone back to Ptx, okay. If you have the next span launched, the power would again reduce. At this point you would put one more amplifier to pull the power back onto Ptx, and that is how you would be able to transmit the optical signals. If the optical amplifier was not there, then the launch Ptx would have to be stopped much before, because if you had let it go all the way here, the sensitivity or the detectivity of the APD or the optical receiver would not be sufficient. So, you have to interrupt the process right before here and then do an optical to electrical conversion, back from electrical to optical conversion, and then pull up the power, okay. So, you can see very well that whereas this is not exactly to the scale, but you can clearly see that you would require multiple such optical to electrical and electrical to optical elements before you would be able to go to the same span length as something that an optical amplifier would provide. This distance before you put in the first repeater or distance before you put the first regenerator is called as a span, or sometimes called as a repeater less span. So, what would be the span or what would be the length of the fiber before you put in the first repeater. So, this is something that an optical amplifier would provide an advantage, okay. Now, semiconductor optical amplifiers was one possible solution, but however it emerged that there was one more solution which was much more robust than the semiconductor optical amplifiers, and it possessed a lot of other advantages that SOAs did not possess, okay. This amplifier was actually made from a fiber material itself. So, it was actually made from a fiber, and in the regular silica fiber you took what are called as these erbium ions, okay. These belong to what is called as a rare earth material, or these are in the periodic table, they are in the rare earth column. So, these erbium ions were doped onto silica fiber. So, silica was the host here and erbium ions were the ones that were being doped. The symbol for erbium is an erbium 3+. These are the ions that you are actually looking at. So, which means that they do come with some electric field, okay. So, or they will at least perturb the electric field of the silica host, changing the overall energy levels, okay. So, these amplifiers which were made of what are called as erbium doped fibers, they became very popular. In fact, these are the reasons why the WDM era simply took off. So, what is it that erbium doped fiber amplifiers had that SOAs lacked? Well, erbium doped fiber amplifiers was very efficient fiber coupled amplifier, okay. So, you did not have to go from a fiber input which was coming from the transmission fiber, convert that fiber into a free space version in order to launch onto the optical amplifier, semiconductor optical amplifier, because semiconductor optical amplifier is a waveguide. So, you have a fiber and you have a waveguide. So, from fiber to waveguide, if you want to couple, there are going to be losses. So, this fiber coupled amplifier or this erbium doped fiber amplifier did not have such a problem, although there is a different kind of a problem. This problem is largely mitigated because your input is fiber and the amplifier material is also in the fiber domain. Okay. So, it was very efficient fiber coupled device, and more importantly it could amplify multiple wavelengths simultaneously. Okay. Although semiconductor optical amplifier can also do this multiple wavelength amplification, it does suffer from certain problems. Okay. It mainly suffers from the problem of crosstalk, and it also suffers from what is called as the gain burning, you know. So, the we'll talk about that one slightly later. Okay. But erbium doped fiber amplifiers could actually amplify multiple wavelengths simultaneously. The gain of these wavelengths were not always the same, okay, but that was a problem that was solved very quickly after the erbium doped fibers were introduced. So, before that, the point to note here is that they were able to amplify all these wavelengths in the so called C band simultaneously, thus giving rise to no requirement of a demultiplexing and then separately amplifying everything. Okay. So, you just put one so whatever the incoming fiber that is there, you just couple it to the erbium doped fiber, pump the erbium doped fiber, and what you get is an amplified signal. All wavelengths are amplified simultaneously, okay, more or less they are all amplified simultaneously. Moreover, erbium doped fiber amplifiers were more or less insensitive to polarization changes of the input. They were also insensitive more or less to the fluctuations in the pump power, whereas these two qualities were completely opposite in the semiconductor optical amplifiers. So, what we will do here would be to first talk about the erbium doped fiber amplifiers in the next few minutes, and then talk about the remaining amplifiers in the next module. Okay. So, let us begin by looking at what an erbium doped fiber amplifier is and how it would amplify the signals. We will not go into a too detailed theory at this point, because although the actual working of an erbium doped fiber amplifier is quite complicated and there are good number of textbooks available for you to fill up that knowledge, from the big picture perspective, an erbium doped fiber amplifier or a semiconductor optical amplifier both operate on the principle of stimulated and spontaneous emission. If you recall what the stimulated and spontaneous emissions were, if you remember, you had materials which had certain energy levels. So, let us say this material had an energy level E1, energy level E2 and an energy level E3. So, I am showing 3 energy levels because that is what is typically found in a erbium doped fiber. So, to these energy levels, you want to pick 2 of those energy levels and create a population inversion. This, of course, being the ground state, will be the first natural part of the 2 level system, and we have to choose between E2 and E3. It turns out that if you choose to pump this erbium doped fiber, okay, with a 980 nanometer pump diode, okay, so this has to be a separate one, this is a pump diode. So, if you were to choose to pump, then all the atoms that are there in the ground level or the ions that are there in the ground level would absorb the photons at 980 nanometer and jump up to level E3. Okay. From this level, they will very quickly within about 1 to 2 microsecond drop down to level E2. So, there is some sort of an indirect pumping going on. So, you take an erbium doped fiber and then you send in a 980 nanometer photon through a pump photodiode, laser diode. This would then excite all the atoms from level 1 to level 3, wherein they will relax. They will not emit anything, they will simply relax in what is called as non-radiative decay. Radiative means they will emit some radiation, non-radiative decay means they will not emit any radiation. So, they will non-radiatively decay down to the level 2 and start increasing the population of level 2 ions. Eventually, once you have a signal input, so let us call this as the signal input, or maybe this is my signal input, then this signal input would also be in terms of photons. These photons are then absorbed by the ions that are there in the second level, and then they will drop down to the ground level emitting a photon. Okay. The larger the number of input photons that you send to a certain extent, the larger would be the number of stimulated emission photons. Okay. So, what would be the result of that? The signal would then be amplified. So, the signal power would be larger than whatever the signal that went in. In this case, the signal is actually a time domain or a time varying waveform which is coming in the 1550 nanometer band. So, erbium doped fibers amplifiers are widely used for C band amplification. Okay. C band is around 1520 to 1600 nanometer. So, in this band your entire DWDM technology is more or less located in this band, and the erbium doped fiber amplifiers can almost simultaneously amplify every wavelength out in this particular case. Now, you know from our discussion on a laser that there are three components to a laser. So, there is actually an amplifier in between. This amplifier is what we called as a active medium. Active medium is the one wherein we can create a population inversion. So, erbium doped fibers are equivalent to an amplifier because, or equivalent to an active medium, because when you pump these erbium ions, these ions will jump through the indirect process and create a population inversion between the energy levels E2 and E1. Okay. So, you have an amplifier or an active medium which is anyway there. The second ingredient of this was that you put this amplifier inside a certain cavity. Why would you put them inside a certain cavity such as a Fabry-Perot cavity in this case? Because you want to provide optical feedback, right. So, you want to provide an optical feedback, and of course, a laser does not really take in any external signals. It relies on the process of spontaneous emission to start the process, but once the spontaneous emission starts, okay, because you have created population inversion, each spontaneously emitted photon would then induce a stimulated emission, and the stimulated emission would further induce stimulated emission because they are all getting reflected or they are all confined by this cavity. So, such a thing was essentially what you had for a laser. Now, all you have to do is you take this same device, okay, of course, here there was a pump. Remember, pump was necessary to create a population inversion. Okay. So, without you creating a population inversion, stimulated emission cannot take place, and whatever the emission that you are going to get will be spontaneous emission and it would not laze. To this laser, what you now do is you simply remove this feedback mechanism, or at least at any rate make this feedback mechanism to be a very weak one. Okay. So, this is my attempt at drawing a very weak feedback mechanism. So, I have converted a laser into an optical amplifier by removing the optical feedback. So, I am removing the optical feedback, or I am at least very minimalistic optical feedback. I have essentially minimized any optical feedback. Okay. Instead, stimulated emission is brought about by supplying an external input signal. So, I supply an external input signal so that I get an amplified external output voltage. Okay. So, what I have written over here is actually P out, and the gain can be written in terms of P out and P in as how much optical power that you obtained at the output compared to what optical power you gave at a certain pump current or a pump value. Okay. So, this same idea is for both SOAs as well as for EDFAs. In EDFA, this is the energy level that you are looking at. Okay. Of course, we have also seen that these energy levels are not really energy levels, they actually form a certain band. There is a quasi continuous discrete levels, they are formed because of the the closely spaced atoms in a dense solid medium, as well as in this particular case you see that you have a quasi continuous discrete levels, and this quasi continuous discrete levels happen simply because each erbium ion that is introduced will cause the splitting of the energy levels. So, this splitting is called as Stark splitting, and to properly appreciate this Stark splitting one has to look at quantum mechanics. We are certainly not going to do that, but just take it on the faith that if you have energy levels, these are not going to be discrete energy levels, but there are going to be certain bands around that discrete energy levels. In fact, band is something that is very important. Okay. If you had a discrete energy level, an active medium with just lines E1 and E2, so I am neglecting E3 because you are only looking at population inversion between E2 and E1. If you had just two lines, then there was only one particular wavelength which this could have amplified. Okay. So, if you have such an amplifier, if you make such an hypothetical amplifier over here, and then you come in with a certain broadband signal. So, this is as a function of wavelength, you come in with certain broadband input signal, then what you would have obtained is only one wavelength that is getting amplified. So, you do not want really to happen this, you do not want this to happen. What you want is, if you have a band of frequencies, that is over which the gain can take place, such is something that happens because of the star splitting of the energy bands, then when you come in with multiple wavelengths, then multiple wavelengths can be amplified. So, this is what you would actually observe in an actual erbium doped fiber, and this bandwidth of the erbium doped fiber is essentially determined by what is the width of this quasi continuous band of energy levels that would be possible when you have a erbium ion doped into the fiber. Okay. So, this is how an erbium doped fiber would work, except that I would like to mention it is not just necessary to have a 980 nanometer pumping, it is possible to actually have another type of pumping. Here this pump goes into a 1480 nanometer, okay, which means that you can take a 1480 nanometer laser and then pump it, so that the atoms do not go to the energy level E3 and then decay, they will directly go to the energy level E2. However, this is not usually done for communication applications, because 980 nanometer pump is very low power case or essentially efficient process. So, for the same pump power, the population inversion that is created with 980 nanometer is much higher compared to the 1480 nanometer. There is, however, the problem with 980 nanometer is that its output power is low, as well as a high power 980 nanometer is actually quite difficult to achieve. That is to say, high power output is quite difficult to achieve. Moreover, this requires a WDM pump coupler. Okay. A pump coupler is a device which actually works something like this. So, you have a 1550 nanometer, which is a signal input port, and you have a 980 nanometer coming from a pump diode, and this pump coupler actually couples these two very different wavelengths. Okay. So, these are called as pump couplers, okay, and then you can give this one to the erbium doped fibers for amplification purposes. So, this is your erbium doped fiber. Okay. So, this process is, while very efficient and therefore widely used in communication purposes, 1480 nanometer actually has its use in high power lasers. Okay. So, when you want a high power laser to be fabricated using a fiber, erbium doped fiber, then you use a 1480 nanometer pump. You also use this 1480 nanometer pump because you do not require a WDM coupler, or the pump coupler is not required, because the same single mode fibers can be used. So, you can just take the erbium doped fiber, you can just connect it to using an ordinary coupler, which is very cheap compared to a WDM pump coupler. Okay. And most importantly, this can be remotely located. So, you can actually put this 1480 nanometer coupler at the transmitter side. Okay. So, you have a 1480 nanometer pump, and this pump co-propagates along the signal. Okay. So, no special pump coupler is required, it is an ordinary coupler that is sufficient, and it would, if you put in an erbium doped fiber here, then this would nicely amplify this particular input. Okay. Amplify this signal input in order to generate the amplified signal output. Okay. So, this is all about erbium doped fiber amplifier. We are going to stop discussing this one and then come back to the other aspects of erbium doped fiber in the next module. Thank you very much.